Assalamualaikum warahmatullahi wabarakatuh and very good day to all. So welcome back to the next video. This video is going to discuss with you on the energy balance in non-reactive system, which is the extension or the continuation from the previous video, from the previous series that I have shared with you. So what we're going to discuss today is we're going to look into the method of performing energy balance in non-reactive system, which is a systematic way of doing that, following the step-by-step procedures. And we're going to look into some new terms such as reference states as well as hypothetical path. So these are the things that I'm going to cover in this particular video series. By the end of this topic, they should be able to perform energy balance for non-reactive system using some reference state and hypothetical path. So in terms of the energy balance, right? If let's say we are making energy balance for certain units such as distillation, heat exchanger, absorption column, and etc., the operating conditions such as the temperature and pressure for process stream, such as the input and the output, may be different at different conditions. Okay, so we're going to have a different uh, inputs, okay, for temperature and pressure at different streams entering and exiting the system. As such, we need to be consistent. We need to be consistent with our calculation, which we require us to take what we call that as reference state, and we are required to do. So what do we need to know about this reference state? The values of energy such as phase, enthalpy, internal energy, we reset it at 0. Okay, so when we use reference state, all the values, because we know that we cannot determine the value of the enthalpy or internal energy, etc. But if let's say we take as a reference state, then we decide that, okay, at this particular reference state, in order for us to calculate the change of enthalpy, the change of internal energy, and so on, it has to be referred to a certain state, and that at that particular state, the values are considered as 0. When we actually wanted to design in terms of um, we want to perform the energy balance, okay, we must refer to the reference state. And then we are asking ourselves as well, for example, like how does the steam table formulated? So the steam table that you have referred earlier, how does it being formulated? As I can tell you earlier, it is not possible to know the actual value of the specific internal energy or enthalpy, but we can determine the change of the properties. For example, like what will be the change from one state to another state? What will be the change from, let's say that a steam at 100 degrees Celsius and superheated steam at 400 degrees Celsius. So we can compare in terms of like what will be the change of enthalpy or internal energy for that. And we, therefore, in order for us to calculate it, we can choose the reference state, which is actually what you found in the steam tables. It is set by the similar procedure. So, for example, like in order for the steam table to be formulated, they have chosen that the reference state is liquid water at the triple point. Okay, for example, which is H2O at 0.01 degrees Celsius and 0.00611 bar. So at that particular point, they set the values of the enthalpy as well as the internal energy is equals to 0. So if let's say you refer to the table B7, for example, to look at the water vapor value at 500 degrees Celsius and 20 bar, the specific internal energy is given at 3,115 kilojoule per kilogram. It means that at that particular temperature, at that particular 500 degrees Celsius and 20 bar, right, the specific internal energy of 3,115 kilojoule per kilogram is relative to the reference state of the water at the triple point, which is at 0.01 degrees Celsius and 0.00611 bar. Okay, so if let's say we set at triple point is equals to 0, so the difference between that to 500 degrees Celsius and 20 bar is the difference of the internal energy, the change of the internal energy is 3115. Okay, so that is why we can get the value over there, which is the specific internal energy at that temperature, 520 bar, because it has a reference state that we have said earlier. To look into this example further, okay, so we were given that suppose water at 300 degrees Celsius and 5 bar is chosen as a reference state at which specific enthalpy is defined to be 0. Okay, relative to this state, what is the specific enthalpy of liquid water at 75 degrees Celsius and 1 bar? What is the specific internal energy of liquid water at 75 degrees Celsius and 1 bar? So this is where actually we want to look at what will be the specific enthalpy and specific internal energy of the liquid water at 75 degrees Celsius and 1 bar, given that now instead of using the triple point as the reference point, we want to use the water at 300 degrees Celsius and 5 bar, becoming the reference state. So let's look at the values that's given. Okay, we know that the initial value here, okay, this is given as the reference state in the steam table, okay, which is at this particular point, which is the triple point. We assume that delta H equals to 0 kilojoule per kilogram. So that is the value given there. We know that as well, if we refer to the steam table, we can get 75 degrees Celsius and 1 bar. It gives the specific enthalpy of 314 kilojoule per kilogram. And at the same time, if let's say you look into the steam table at 300 degrees Celsius and 5 bar, it will give you specific internal energy of 3065 kilojoule per kilogram. But right now, in the question here, this is given as the new reference state. Okay, so when this is given as a new reference state, hence, okay, you have to set this value at equals to 0. But you know that the initial value of this is 3065 and this is 314. So as such, you have to measure that what will be the change from 300 degrees Celsius and 5 bar to become 75 degrees Celsius and 1 bar. And you remember that when there is a change of temperature from higher temperature to a lower temperature, you should anticipate that the internal energy or the enthalpy, the change of it will become negative. Okay, because if you remember about the graph here that I have shared you in the previous video, that enthalpy, it will increase with temperature. So if this is temperature and then this is enthalpy, it will increase within temperature. At certain temperature, it change of phase. So again, it still increase, and then it will increase again with increasing. It's supposed to be enthalpy. It's supposed to be temperature. So with increasing temperature, there is an increase of enthalpy, and then there is a change of phase, and again there is a change of temperature. There is an increase of enthalpy, and then there is another change of phase, and then furthermore it will increase. The enthalpy will increase. But right now, you were given that, let's say this is 300 degrees Celsius, okay, and let's say this is 50 bar, but you want it right now, you want to measure the enthalpy at 75 degrees Celsius. Okay, so you know that you want to change, you want to calculate what will be the enthalpy change here, delta H here, right? So now you pick this point as your reference state. So whenever that it become reference state, the value of H here, specific enthalpy, is equals to 0. So of course, you will end up to get a negative value because there is a change of temperature from 300 degrees Celsius to 75 degrees Celsius. Okay, so that is the function of reference state. We will use a lot of reference state after this when we want to perform some kind of calculation.